All right, thank you. I would like to acknowledge a couple of students working currently in the lab, Redmayne and Santiago. They did quite a bit of the hard labor for the project that I'm going to be describing in here. Actually, this is ongoing. Samples have been monitoring even before I joined FAU. We'll talk to you about that. But I would like to acknowledge both 3D URLE and Florida Department of Transportation, as well as Florida Atlantic University. So Pierre already mentioned about this slide, so I'm not going to spend too much time other than to mention that typically in a marine environment, we expect the splash zone to be the one with the worst corrosion. In this case, this is in the intercoastal, right next to where we have our campus, Denia Beach. And for some reason, that didn't take place in there. But as he mentioned, you can see that due to chloride deposition, there are number of piles as well as the cap of this that is undergoing a spill. And I should have included the picture from the other side because it's a lot worse than what you see on this side. But in any event, let me go to the next. In this particular project, we focus on binary samples that were prepared with fly ash and others with silica fume. So these are two commonly used supplementary cementitious materials in Florida. It's a little harder now to get fly ash, but at the time that these samples were prepared, it was being used quite a bit. And Pierre already mentioned that typically in a partially immersed structure, we are going to have the chlorides need to penetrate, reach the rebar, and several speakers mentioned yesterday, this is your typical time to corrosion initiation. But what I would like to introduce in here, more recently, some researchers like Melchers in Australia, as well as Mr. Green, who also is in Australia, have proposed that there is, right after the time to initiation, likely you can observe metastable pitting as well as limited corrosion taking place. Eventually, the corrosion becomes more persistent, and therefore that is the region that now they are calling active corrosion. And we have observed some of that in the samples that I'm going to be describing in here today. I'm not going to take too long to describe the different compositions, just to let you know that there were 4 different mixes that contain fly ash ranging from 20% to 50%. And there were a couple of them that had only Portland cement, but one had also inhibitor added to it. And then there were 4 compositions that contain silica fume. But in this case, these samples were prepared in the 1990s and 1994. And the silica fume is in a slurry form, not in a powdery form. So there was some water that was counted to the water to cementitious. That's the other thing. All of these samples were prepared with a 0.37 water to cementitious ratio. All right, and during the from 1994 to 2018 or so, they were subjected to wet and dry cycles, 1 week without, with seawater. I ran out of students that wanted to do this kind of pro bono. So during about 3 years, we interrupted the adding of the seawater. And these samples are exposed outdoors, you'll see in a moment. But when we started the first year of the 3D URLE project, we reinitiated the wetting with seawater, but just not as frequently as we used to do before. And these are geometry of the samples and an old picture of the samples. And you can see that most of the samples have 1.9 centimeters concrete cover, or 3/4 of an inch. And a few of them had 1.25 inches of concrete cover, or 3.2 centimeters. Most of the samples that actually going to be describing today had a concrete cover of 1.9. And over the years, we have terminated samples. We terminated some after about 5,600 days, others after 6,200 days. and the previous effort was about 8,000 days. So from the table that you see here, we don't have all of those samples anymore, but we still have a large number that we thought that was interesting to see what happened, what was the condition after 10,000 days, and actually some of them were terminated as part of this effort. So we did, starting in late 2020, we did galvanostatic pulse by using a potential stat, and we were taking that outside. So in that case, since we didn't know what was the corroding area, we are going to show you the values, typical values in corrosion current rather than corrosion current density. But then we had on loan HECOR from a G-core from the FDOT. So during 2022, we did several measurements. And actually, before terminating some of the samples, we did also these measurements, and I will discuss that briefly. So selected rebars were selected for forensic analysis, and in some cases, we only terminated one. So from the diagram that I show you here, if we found that the crack was only above this rebar, then we did a longitudinal cut, and we only exposed the rebar that is on the right. We also did 2 additional transverse coat without touching the rebar, and then we apply a chisel to open up and remove the top, so we can observe the surface condition. In some cases where we remove either 2 or 3 rebars, we also core the specimens. So we did some visual inspections for those that were terminated. We also used conical caliper to try to estimate what was the cross-section loss. And as I was telling you, in some cases we core, and then we had several layers, and we were able to obtain the chloride profile. And also from the piece of concrete that was right above the rebar, if the corrosion products were not all along the sample, then we did milling, and we obtained estimated amount of what was the chloride concentration right at the rebar trace for some specimens as well. So these are a more recent picture of the samples. Here is in a sunny day. You can see that the cover that I showed in the previous picture was no longer there. Here are some of the results from the monitoring using the galvanostatic pulse for a couple of samples. On the left is one that contained 20% fly ash, and you can see that all the magnitude of the current was larger than 100 microamps over the whole period, and reached situations where we're up to 500. And the corresponding potential, these values are versus calomel. So you like to have these versus copper sulfate, you need to shift it 70 millivolts more negative. And in here, there is one that contains silica fume. In actually these particular specimens, we actually apply electromagation to add chlorides to go into the concrete. So in this case, you can see that the current observed range anywhere between 200, in some cases exceeded 1,000 microamps. And the corresponding potential at later times were more negative than 500 versus calomel, which means that it's close to minus 600 versus copper sulfate. As I was mentioning, we used the HECOR during 2022. And here I'm showing you the relationship between the corrosion potential and the corrosion rate. On the one on the left, we have some samples that were later terminated that are no longer included on the picture on the right. But you can see that there is kind of a trend, as is expected, as the potential increases, the corrosion rate increases, but it's not perfect. There are situations where you can have relatively positive potential and low corrosion current as expected, but in other cases, at that same low or no potential, you observe situations where the corrosion current density is ongoing. And that might be because the area that is corroding is polarized by the area not corroding, and that's why we observe these more positive potentials. So these are examples of the chloride profiles, and as I told you, in this case, we did do some electromigration, and the chloride concentration, the river in this case was 19 centimeters, or sorry, 19 millimeters. And unfortunately, the corrosion, I'll show you in a moment, was covered most of the length, so we don't have a value at the river trace. But whereas for this other sample, actually this is a thicker concrete cover, and you can see that right at the river trace, the concentration is larger than that observed from the core. And that we have reported this with a work that we did when I was doing my PhD with Dr. Sagüez, and also Dr. Hart at FAU has reported that the presence of the rebar actually increases what is the concentration that you find on the river trace right above the river compared to what you observe from a core. And okay, so let me go really quickly on some of these results. So here are some images of the cracks that were observed on SF1, and the corrosion products right after we open it, and then what is the rebar surface after we clean it. I'm going to go through some of them, just a few additional situations. In this case, what we did, we used walnut sand to clean the rebars. And here is an example of the cross-section loss as a function of length. And there is this region, I'm showing you this on the right, but actually with respect to this picture, the corroding side is here on the left side. So here is an additional example of that. We calculated what is called the pitting factor, but we did this slightly different from what it is typically done. We obtained the maximum change in the area with respect to the average of the change in the area only on the corroding region. Others have calculated this with respect to the original diameter or the area of the rebar. And we also calculated what is the average corrosion-induced mass loss. Since we measured where the corrosion took place, we know what was the loss in the diameter. We can estimate what is the updated mass of the corroding rebar with respect to the initial mass of the rebar, and that if we are calling eta. So let me show you, well, I'm going to skip that because of time constraints. Here is the table showing you all the rebars that we opened as part of this project, and the corresponding eta values, pitting factor values, and the electrochemical measurements right before the samples were terminated. I'm going to take a moment to show you that in some cases you can have relatively high resistivities and relatively high corrosion rates, whereas in other cases with the same concrete composition, you can have low resistivities with even modest corrosion rates in this case. But the reason for that is that likely this particular specimen had a larger crack, so the measured resistivity is smaller with the solution that is in the structure. So here are a couple of additional plots showing the relationship between the eta and the corrosion rate. For the green symbols and the blue symbols are for the samples that were obtained as part of this project, and the empty circles are some that were done before. So it is possible that now that these samples are older, some of the corrosion rate are larger and comparable mass loss, average mass loss observed. And we also plotted the resistivity versus the eta value, and you see again that there is quite a bit of a spread of these values, and it is expected that in this case it's not really the concrete resistivity that we are measuring, but it's based as to what is the with including the presence of cracks that were in the samples where we did these measurements. And not going to bore you reading the conclusions. Thank you for your attention. I'll be happy to answer any questions. And of course, the disclaimer, these are my opinions and not those of the FDOT or those of the TrueDure LE. Thank you. Yes.
Okay, interesting. I wonder now that the outside.
Yeah, so the samples that we have inside, what we did, we accelerate the chloride transport, so we shortened the time to initiation, but we are not accelerating the corrosion propagation of the samples that we have indoors. So it's likely that the corrosion propagation, there is one sample that recently we observed that have cracks. It can take anywhere between 5 and 6 years for you to observe the crack, even on those samples that are indoors. But yeah, the idea was try to do that. And I didn't talk too much about this, but there are a couple of the black dots in here. Those are laboratory samples that appear that are in alignment with those from the outdoor exposure. All right.